In the next two sections, what we do is we take this idea of systems of inequalities and we develop the idea of linear programming. Now, linear programming is going to be a big topic of the semester. Later on, we'll deal with it and use matrices, but right now we're going to study how to solve it graphically. And in 3.4, all it is applications of what we're going to do, so I've combined the sections. So really what you do is you have a system of inequalities that define constraints. Those are rules that your variables have to follow. And you have some kind of objective function, maybe it's profit. And so you either want to maybe maximize the profit according to these constraints. So you can only make so many of these, you only have a budget of this. Or maybe you want to minimize cost according to some kind of constraints. And we have a fundamental theorem that tells us the optimal value, so the maximum or minimum, is going to occur at corner points of the feasible region. So just like we saw before. So what we could do is we could graph the feasible region, figure out the corner points, and then figure out where our objective function is either largest or smallest at which of the corner points. And this theorem guarantees that the answer for the whole system, the optimal value, will occur at one of those corner points. So I think it's best to jump right into an example. Some of the steps I'm going to leave out, but some of them I'll be showing you. So we did some of the work of this before. Just for language sake, just so we all know what we're talking about, this value right here, the function we're trying to minimize or maximize, this is the objective function. Subject to, and these are our constraints. It turns out that this constraint right here is very special. You'll see it come up quite a bit. And that constraint keeps us in that first quadrant, if you remember. Well, the first thing I did was I numbered all of these so I could keep track when I'm graphing. And then I went through and I rewrote them so that I had the y first, because this will tell me the directions of my inequalities. And so you can double check, but I got 20 minus 2x. For 2, I ended up with y is greater than or equal to 36 minus 10x. And for 3, I ended up with y is greater than or equal to 7.2 minus 2/5 x. All right, so remember for each of these, what I want to find is an x-intercept, right, and a y-intercept. And so for 1, my x-intercept is going to be 10, and my y-intercept is going to be 20. For 2, my x-intercept, now I'm going to go ahead and actually leave this in decimal form as 3.6, and my y-intercept is 36. Got to be careful when I'm reading this, right? That's got to be very careful. And here my x-intercept is 18, and my y-intercept is 7.2. Okay, and those are all found the same way we did before. You notice I don't have a grid over here because I knew my scale might be kind of crazy. Not too bad. I got to get out to 36. So I could do something like count by 5s and go out to 40 or something like that, right? Now, once again, I'm going to draw only the first quadrant. So with my y and x being positive, I know that I don't care about what happens below the x-axis or to the left of the y-axis. So there's my axes, and I'm interested in the first quadrant. Okay, and again, I got to pick a scale. I think I'm going to count by 5s. And go out to 40 on both. So this is 5, 10, 15, etc. So you always want to label this so that people that look at your graph know exactly what you did. All right, so now I'm ready to graph. Okay, with number 1, my x-intercept is 10. I'll mark that right here, and my y-intercept is 20. And remember, I don't have to graph the whole line since we have to be positive, and I can just worry about this quadrant. So there's my line, right? Not a perfect line, a little bit easier to draw on paper, but we got the general idea. Okay, I'm going to label that. This is 1, and this is y equals 20 minus 2x. I'll need that later on when I'm looking at the graph on the calculator. Okay, and now I want to do 2. So I'll do 2 in red. And my x-intercept is 3.6, so way low. But this has a really steep slope, and so because it has a slope of 10, we have to go all the way up to 36 up here. Okay, so I want to connect those two values and draw my line. Almost a straight line down, and so this is 2, and that line represents y equals 36 minus 10x. Okay, and then finally I want to graph 3. I'll use green for that, and we have a y-intercept of 7.2, so maybe about right here, and an x-intercept of 18, so way out here. All right, so I want to connect those two lines, and then I got to really think about this, because notice that my constraints have greater thans and less thans. All right, and so this last line I can label out here. This is 3, and it represents 7.2 minus 2/5 x. I totally believe that being able to solve these problems isn't about mathematical ability, because we're doing things that we all learned before. It's about being organized, and that's really it, and paying attention to a little bit of new vocabulary, but we got to be organized. Now the question is, which of these regions represents my feasible region? I got to be careful again. We got to be below line 1. Okay, so we got to be below line 1. I'm going to put a little mark there to remember that. So below line 1. Okay, so kind of made a little arrow. Okay, below line 1, below line 1. All right, we got to be above line 2 because it's a greater than or equal. So line 2 was in red, so we got to be above line 2. So now we can't be over here because that's below line 2, even though it's below line 1 like we want. We have to have all these overlap. And then for 3, we need to be above that line because it's a greater than. So we got to also be above this. So if you look at all these regions, only one satisfies all of these properties, and it would be the one right in here. One technique you could do is shade each of these with a lighter or darker pencil. So shade below line 1, shade above line 2 and above line 3, and see where they all overlap. That can be much easier to see sometimes. But there's our feasible region. Okay, well, what's next? We're trying to maximize and minimize this function right here. Remember, our fundamental theorem says that the max or min is going to occur at a corner point. So we got to figure out where corner points are. Corner points are lines of intersection or points of intersection in your feasible region. So it's points outlining that feasible region. If I was to look here, we have 1, 2, 3 corner points. I'm going to call these A, B, and C, just so I can keep track. We got to figure out what A, B, and C are so that we can figure out which one makes Z maximum and which one makes Z minimum. What I'll also start here is I'll start a corner point table, and I'll start finding values of Z for each corner point. So we're going to have corner point A, B, and C. All right, so to find corner point A, you could set line 2 equal to line 3 and solve, and that's fine. But I'm going to do this on the calculator. It's a little bit quicker. So what I do is I type in all the lines that I have. It doesn't matter which one you use as 1, 2, and 3, although maybe it helps to be in the same order as you started with when you were drawing the problem. And then once I have all those lines entered, I'm going to go to graph. Now, if my graph doesn't come out nice, and in fact, maybe I'll just do this right now. I'm going to press instead zoom. And I'm going to go to zoom standard, number 6. Now, if you notice when it graphs like this, I actually am missing part of the graph, right? The first thing I'm looking is to make sure it looks basically like I did. And you may say, why not do the whole thing on the calculator? The problem is getting that feasible region to come out nicely. Right here, maybe it wouldn't be so bad, but when you have 5 or 6 inequalities, it can be kind of tough. So I'm missing some of this. So what I'm going to do is go to Window and Adjust. It has X-min at -10. I'm going to change that to 0 because, or it has X-min, and I want to change that to 0 because we have to be positive. And I think I need a higher X max. I'm going to make it look just like mine. I'm going to go up 40 and Y min 0, and I'm going to go up Y max up to 40. Now I'm going to hit graph. And I'm going to see all the lines just like I have them. If something looks majorly different, then I know I messed up. All right, so as we did before, to find the intersection point, I'm going to go to second and calculate. I'm going to go to intersect number 5, and it'll ask me the first curve, second curve, etc. If you look at the equation up on the very top, you got to pay attention to that. So for A, we want it to be the red line, so 36 minus 10x. Okay, I found that. Press enter once you find that. And then the green line, which for me, I'm going to press around, is 7.2 minus 2/5 x. Whatever it says for guess, press enter. And so I get 3, 6. I'm going to do the same thing now. I'm going to go back to the second calculate. I'm going to go back to number 5. And now I'm going to find point B. And so that's on the line 20 minus 2x and 36 minus 10x. Press enter, whatever it says guess, and I got 2, 16. And then finally for C, that's the intersection of the blue line and the green line. So the blue line is 20 minus 2x. So I go back, say, okay, I want 20 minus 2x, and I want 7.2. You might have to press up or down, minus 2/5 x. So pay attention to the top, what it says. Whatever it says to guess, guess. And I got 8, 4. You can see that that'd probably be pretty tough to read off of your typical graph that's hand-drawn. All right, so there were 3 corner points, and the max or min is going to occur on one of these points. So what I'll do is now plug these in. And so remember, z equals 3x plus y. So here this would be 3 times 3 is 9, plus 6, I get 15. 3 times 2, so I'm plugging it in up here. 3 times 2 is 6, plus 16 is 22. And 3 times 8 is 24, plus 4 is 28. All right, I found my max, and I found my min. Well, how do I write that down? So what I could say is z is maximized at the point 8, 4, and has a max value of 28. Okay, so that's the first one. That's the maximized part. What about the minimize? Another way to write it, so I'll show you just another way to write it. We'll put it up here because I'm running low on space. We'll say the min is 15, and it occurs at, and we'll say it occurs at 3, 6. So if I'm maximizing and minimizing, both of those would be answers. So I'd want to circle them. So you can see linear programming is really a deep analysis of a problem, and we're finding a lot of information, but it's all about those corner points. That's really the goal of everything we're doing, is finding those corner points. Your max or min will always occur at the corner point. So your goal is graph the inequalities, figure out what those corner points are, and then your max or min is going to occur at one of them. So let's take a look at an applied problem and see how this actually works when you're dealing with more realistic numbers. Okay, so we have a company that makes hair dryers, 2 types, petite and deluxe. Okay, we're given the amount of labor it takes to make each of them. We're given the amount of profit we make off of each of them. And I'm still reading. Let's see, we have a limited number of labor hours, and we have a certain budget. Okay, we want to maximize profit. We want to set this up as a linear programming problem because we're asked to maximize something. So I want to write that down. We're maximizing profit. So I want to write a z function that represents profit, and I need my variables now. So we make 2 types of hair dryers. So what I'll do is I'll say, okay, x is going to be the number of petite we should make, and y is going to be the number of deluxe we should make. So my z is going to be in terms of that. Now, if I'm going to read through again, it says the materials cost, blah, 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 while the profit, there we go. While the profit is $5 for petite. So every time I make petite one, I get $5, or every time I sell it, and then $6 for the deluxe. Okay, so we want to maximize this. And now we have constraints, so we have budgets and stuff. So this is subject to, all right, what's our first constraint? If we go in order, we're given a limited number of labor hours, right? We can't exceed the number of labor hours. And it says it requires 1 hour of labor to make the petite. So 1 times x is just x. But my total labor hours are going to be for both. The deluxe, it takes 2 hours. And you can't use up more labor hours than you have, so $39.50. Okay, now what about materials budget? I can't exceed that, right? But it could equal It says materials cost $4 for each petite and $3 for each deluxe. So when I combine them, I don't want to exceed my weekly budget, $95.75. So this will be how many I should make each week. And then finally, an obvious one that's easy to forget, I can't make negative number, right? So this would actually be my linear programming problem right here. But we want to solve this. We want to figure out how many we should make to make the maximum profit with these constraints. I'm not going to do this any differently than I did before. In other words, the first thing I'm going to do is solve my inequalities, my constraints for y. When I do that, I get the following. So for 1, I have y is less than or equal to 1975 minus 1/2 x. And for 2, I end up with y is less than or equal to 3191.7 minus 4/3 x. Okay, so I got my inequality set up, and now I need to figure out intercepts, right? The y-intercept's pretty easy because here and here it's just given. Let's see what the other ones are. So for 1, I get an x-intercept. If you were to double check this, you get 3950. A y-intercept, 1975. And then for 2, you get an x-intercept of 23, and I'm going to round 2393.8, and a y-intercept of 3191.7. So both of those are rounded, but remember, we're going to use the calculator to find the corner points. This is to visualize the situation. Now I got to think of my scale when I graph this. I'm only going to graph the positive side. It looks like I should go out to 4,000, and it looks like reasonably I could count by 500s. These are all pretty close. And so that's what I'm going to do. I'm going to make my x and y scale. And again, because I have the constraints that both have to be positive, I can go ahead and just focus in on the first quadrant. So here's my x, here's my y. And so I got 1, 2, 3, 4,000. And 1, 2, 3, 4,000. Okay, so I'll graph 1 in blue. We go from 3950, so that'd be way out here, to 1975. So that's almost 2,000, so maybe about right here. So there's my first inequality. Now I want to make sure to label that, so this would be 1. And remember, this is the line y equals 1975 minus 1/2 x. Okay, for the next one, I'll do this one in red. And so for 2, we have an x-intercept of 2393. So if this is 2,000, that's 3,000, maybe we're about right here. 2393, and for the y-intercept of 3191. So this is 3,000, so maybe about right here. Okay, once again, I want to connect these because remember, where they cross is going to be important. It's probably a corner point. They're not my best line, but we got the idea. Okay, so I'm going to label this one. This is 2. Y equals 3191.7 minus 4/3 x. Okay, just in case I need that information. Notice that both of these are less than or equal, so we got to be below both of them. The only way to be below both of them but above the axes would be to be in this region right here. And I can also see here's a corner point, here's a corner point, here's a corner point, and here's a corner point. Now, several of these corner points are easy to find. This corner point is the y-intercept of 1. We just found it a second ago, right? Because that's how we drew the line. So this would actually be the point 0, 1975. This point right here, easy, 0, 0. Probably won't maximize profit to make nothing, so I can probably ignore that one overall. This point out here, this is the x-intercept of line 2. And so this would be 2393.8. 0. And so the only one we got to find is this one right here, and we can actually find that in the calculator. So I'm going to go in the calculator and I'm going to type both of these in. I got to clear anything I had before. And so the first one again, 1975 minus 1/2 x. Make sure you put your 1/2 in parentheses. And the next one, 3191.7 minus parentheses 4/3, close parentheses x. This time I'm just going to go to graph and see how it comes out. I have my old rules on there though, so it's probably not going to come out good. And so what do you do when something like this happens? Your best bet is to go in and adjust the window yourself. If you notice, we went out to 4,000. That's what I'm going to do. So 0 out to 4,000 and 0 out to 4,000. So I go to graph, making sure my lines look basically like what I have. And I got them. So now I can calculate that intersection point. So I go to second, calc, number 5. This time, since there's only 2 lines, I can basically enter through everything. And I get this point as 1460, comma, let's say 1245, we'll round. So the maximum value occurs at one of these points, And so it could be at this point, it could be at this point. Most often it's going to be at this outer point, but it actually depends on the situation, so you shouldn't assume that that's the case. So what I'll do is I'll go ahead and make my table, and this time it's profit, right? So it's profit, and then our corner point. Okay, so for 0, 0, let's get that out of the way. If I plug that in to right here, it's 5 times 0 plus 6 times 0. That's 0, so we kind of knew that. All right, so now I'm going to do this. So I checked that one. I'm going to check this one now. 0, comma, 1975. So there's no x. It would just be 6 times 1975. So I get 11,850 as the weekly profit. If we just, so that would mean that we are making 1,975 of whatever y was. That'd be deluxe. So that'd mean if we were only making deluxe, this is how much we would make. Okay, the next corner point I'll try is this one right here. This would be where we're making approximately, and so I'll put the approximation since we can't have really decimals, 2394, comma 0. So we're making just 2,300 plus, so almost 2,400 of the petites. And so if I plug that in for x and y with my z, I get 5 times 2394 plus 0 times 6. So I just end up with 11,970. So it's slightly increased. So it's a little bit better to make only petites. Now the last corner point we found was 1460, comma 1245. Okay, so it'd be 5 times 1460 plus 6 times 1245. I get 14,770, definitely the maximum, right? So I found my maximum point, but what I need to do is translate this into the problem. So we should make 1,460, whatever x was, petites, and 1245, whatever y was, which were deluxes, to maximize profit. And if I said, what is the maximum profit? You would tell me it's $14,770. So as you can see, this will work even for applied problems. Don't fall into the habit of thinking this will always be your max. There's definitely some cases where it's not, but you'll see that pop up quite a bit. But with this analysis, I've now decided how much is optimal to make. And it, again, in a real life situation, this is much more realistic than our equations we dealt with before because I have constraints on things.